Hi friends, after completion of center of mass, now we can move further to the new topic, that is rotation. Today I will introduce you the terminology of rotation and how the basic questions can be solved from this topic. So let us start. Rotational kinematics. Till now we had considered that all the particles, all the bodies are like particle only. For this purpose only, we had derived the concept of center of mass also, so that the rigid body can be replaced by a particle mass. But now we have to consider shape and size of body as well. And then this topic rotation starts. In rotation, we cannot ignore the size and shape of body. So let us first consider, very oftenly I am using the word rigid body. What is rigid body? Why is it called rigid? Rigid body is something in which relative separation between any two consecutive particles cannot change with application of force. So if it is the case that relative position is not changing between two constituent particles, then we can say that this given body is a rigid body. Now onwards we have to study about this kind of body for which shape and size has to be considered, which comes under the topic rotation. Now what kind of motion is rotation? Let us consider that it is a rigid body which is rotating about, as the motion is rotation here, so which is rotating about this axis Z. Now what kind of motion its constituent particles will be having? Let us consider one particle A to be here, another particle B to be here. So if this whole body is rotating about Z axis, A will be moving in this circular plane about the axis, B also will be moving in a circle about the axis Z. So we can say that if a body is in rotation about a given axis, then all the constituent particles will move in circle along that axis. This kind of motion is rotation. Now we have to also know that a particle cannot have rotation. It can have only translation. Even if translation is along a curve, that is okay, but particle cannot participate in kind of motion, that is rotation. Because for rotation we are saying that the whole body is rotating about an axis and all the constituent particles are moving along circles. And if it is only one particle, then how can we explain this kind of motion? There will be no constituent particles, only a single particle will be here. So we can say that a particle cannot have rotation, whereas a body can have both kind of motion, that is translation plus rotation. So this is the basic difference between rotation and translation. Now let us concentrate to rotational kinematics. Here again we have to consider only the motion without bothering about its cause. So if we consider only the rotational kind of motion, then we can see that all the particles which are on the axis will not move at all, or we can say they have zero velocity. So all the particles which lie on the rotational axis will have zero velocity, and all other particles will be having velocity given by v is equal to omega r, where r is distance of that particular point with respect to the rotation axis. And of course omega has to be same for all the particles, because if omega is different, let us consider a situation here. Let this be a particle A which is rotating about, this being the rotational axis. Let after time t, A has come to this point, so it is making angle theta with respect to its initial position. Now if another particle is here, let that be B in the same line as A, then in time t, this also has to swipe through the same angle, because if this angle is not same, these are the new positions of A and B, that is given by A dashed and B dashed. If theta is not same for these two particles, then of course there will be relative separation between the particles changed, which is not possible in case of a rigid body. That is why we always say that omega has to be, it is not constant, but it has to be same for the whole body. For every particle this has to be same, and for the same reason we can say that alpha has to be also same for the whole body, all the constituent particles. Now we got two things, that omega should be same and alpha should be same. But what about the linear velocity and the linear acceleration? If we write, already we have derived this in circular motion, because each constituent particle is moving along a circle, so its velocity can be given by expression we had derived in circular motion, that is equal to omega r, where r is position of that particle with respect to axis of rotation. And similarly we can say that tangential acceleration also can be written as alpha r. So these are the two relations we have to consider. And as in linear kinematics, again the same definitions are here. Like for angular velocity we have to write d theta by dt, and if it is average then it can be written as delta theta by delta t. The same for angular acceleration, as in linear kinematics it has to be now d omega by dt is equal to delta omega by delta t if written for a large time span. So we can see that all the expressions and equations in kinematics are same whether it is for linear or for rotational motion. And we can of course apply for constant acceleration. Here alpha has to be constant. So for constant alpha we can write all the three kinematical equations. What it will be? Omega is equal to omega naught plus alpha t. Second being delta theta is equal to omega naught t plus half alpha t square. And the third one, omega square is equal to omega naught square plus 2 alpha delta theta. These are the three similar equations we had written for translational kinematics. It has to be used again here also. Now what about the direction of these kinematical terms here? Now see, change in, because we are writing that omega is equal to d theta by dt. So direction of omega has to be along direction of change in angle, and direction of change in angle has to be always perpendicular to the plane in which the rotation is taking place. So omega also be in the direction perpendicular to plane of rotation. Conventionally it is taken as outward towards the viewer if the rotation is anti-clockwise and inward. So in this way direction of omega is written. Similar is the explanation for direction of alpha, that has to be equal to d omega by dt. Here alpha can have only two direction, either in direction of omega or opposite to it, because if omega is increasing with time, alpha has to be positive and it will be in the direction of omega. If omega is decreasing with time, alpha will be in direction opposite to that of omega. So here direction of omega and alpha always has to be perpendicular to the plane of rotation. This point has to be remembered very well. Now let us see how questions can be solved from rotational kinematics. A very new concept. Already we have solved questions from translational kinematics. So let us see what few changes are there in rotational kinematics. The first example is I have taken the motor of an engine is rotating about its axis with an angular velocity of 100 revolution per minute. So this is the initial velocity. Now here it is given in terms of revolution per minute. So of course while writing in SI it has to be converted to radian per second. So how will it be converted? In one rotation total angle made is 2 pi. So 100 multiplied by 2 pi, and it has to be divided with 60 to get the value per second. And it is coming to rest in 15 seconds. So t is given 15 seconds. Assuming constant angular deceleration, calculate the number of revolutions made by it before coming to rest. Finally, it has come to a stop. So final omega has to be equal to 0. Now, as deceleration is constant, so we can simply apply the equation for constant angular acceleration. That can be written here as final velocity omega to be equal to omega naught plus alpha t. Let us substitute the values. 0 is equal to omega naught is given there, 100 into 2 pi upon 60, minus because deceleration is taking place, so minus alpha into 15. We will get value of alpha from here, that will be equal to 2 pi by 9 radian per second square. Now after getting this value, we can now calculate number of revolutions made. Okay, so total number of revolution, if it is n, then total angle made has to be equal to n into 2 pi, which can be written in place of delta theta. So delta theta is equal to omega naught t plus half alpha t square. This will be equal to 100 into 2 pi by 60 into 15, minus alpha is negative here, so minus half 2 pi by 9 into square of 15. On solving this, we will get 25 pi radian. So from here we got n to be equal to 25 upon 2 pi, that is equal to 12.5 revolution. So this is the total number of revolutions made before the motor has come to rest. One more example is there. Starting from rest, a fan takes 5 seconds to attain the maximum speed of 400 rotation per minute. Again omega is given, that is 400 rotation per minute. It has to be multiplied with 2 pi to get the value in radian and divided by 60 to get the value in second. Assuming constant acceleration, find the time taken by fan in attaining half the maximum speed. Now we can write omega is equal to omega naught plus alpha t. So this can be written as 400 into 2 pi upon 60 equal to 0 plus alpha. Time is taken as 5 seconds, so it has to be multiplied with 5. On solving this, we will get the value of alpha. Now in next equation we can write, because it is asking for time taken to attain half the maximum speed. So here now half the maximum speed has to be equal to 200 revolution per minute. So 200 is taken as omega, 200 into 2 pi by 60 is equal to omega naught, that is 0, plus alpha. Now I can directly substitute value of alpha from above equation, that is 400 into 2 pi upon 60 into 5t. And on solving, these two got cancelled. We will get t to be equal to 5 by 2 second, which is 2.5 second. It is obvious from question itself, because angular velocity is changing linearly. So of course it will take only half the time to reach the half of maximum speed. One more we have, a wheel rotates with an angular acceleration given by alpha is equal to 480 cube. Here alpha is given as 480 cube minus 3bt square, where a and b are constants. If the wheel has initial angular speed omega naught, write the equations for angular speed and angular displacement. Okay, alpha is given here, so it can be written as d omega by dt. That will be equal to 480 cube minus 3bt square. And then we can write d omega to be equal to 480 cube minus 3bt square, and this whole multiplied with dt. If we integrate the equations, time has to start from 0 to t, and initial angular speed is given as omega naught. So omega naught to omega we have to write. Here we have to write only the general expression. So final limit should not be taken as constant. Now we will get omega minus omega naught to be equal to 4a. It will be t4 upon 4. These two got cancelled. Minus 3b t cube upon 3. These two also got cancelled. And finally omega is equal to omega naught plus a t4 minus b t cube. This is the expression of omega we have got. Next it is asking for angular displacement. Now omega can be written as d theta by dt. So from here we can write d theta by dt to be equal to omega, which we have just derived, that is omega naught plus at4 minus bt cube. And on solving, d theta is equal to omega naught plus at4 minus bt cube, this whole multiplied with dt. On integrating both the sides, and it has started rotating, so of course initial theta has to be 0, initial time also 0, and integrate within the limits 0 to theta and 0 to t. We will get theta to be equal to omega naught t plus a t5 upon 5 minus b t4 upon 4. This is the expression for angular displacement which is desired. Let us solve one example. When a torque acting upon a system is 0, which of the following will be constant? Different options are given here. First is force, second is linear impulse, third is linear momentum, and the fourth is angular momentum. Now this question is purely conceptual. If you have learned the concept properly, you can answer this question. What it is saying here, that torque acting on the system is 0. So if torque on a system is 0, and as we know that torque is defined as dl by dt, that is rate of change of angular momentum. So if torque is 0, dl by dt has to be equal to 0. And what is dl by dt? This is rate of change of angular momentum. It implies that angular momentum has to be constant. So L will be constant if torque is 0. As we know, on differentiating a constant term, we get the value 0. So correct option will be option number D. Whereas in the question, if it is written that a force is 0 which is acting on the system, then it can be said that linear momentum of system will remain constant. Now this one is very interesting question with a newer concept. A uniform bar AB of length 50 cm rotates counterclockwise about point A with constant angular speed. At the instant shown, the linear speed Vc of center of mass is 7.5 cm per second. What are the angular speed and angular velocity of the bar? And then what is linear velocity of point B? Okay, let us start with the first one. The angular speed and the angular velocity of bar. Now, since here linear speed of point C is given, that is equal to 7.5 cm per second. So, Vc can be written as omega r as we had derived, and from here we can write value of omega to be equal to Vc upon r. On substituting this, it will come out to be 7.5 upon r, as it is at the center, so it has to be 25. This will come out to be 0.3 radian per second. It is rotating in the given xy plane, so we can write directly r to be equal to 25 cm. Now angular velocity should be, because it is rotating in xy plane, so angular velocity should be always perpendicular to the plane. So if we write in vector form, that should be 0.3. Now let us check for the direction of rotation. It is in anti-clockwise direction, so has to be taken as towards the viewer, that can be written as z direction. So this is the vector representation of omega. Direction will be along z axis. Now speed of point B it is asking. So Vb can be written as, again we can write omega r for B, that will be equal to 50 into 0.3. Omega has to be same for all the points, that will be equal to 15 cm per second. This is velocity of B, and for any point velocity has to be along the tangent, so it has to be in this direction. So if we write in vector form, Vb can be written as, now what angle it will make with x-axis, as you can see from here, this is 30 degrees, so it has to be 60 degree. So we got minus 15 cos 60 degree I plus 15 sin 60 degree j. So this is speed and velocity of point B, and angular speed and angular velocity for the whole rod. Now, after doing a number of questions from rotational kinematics, we are coming to the part that is dynamics. Now, we cannot ignore the cause of motion, which is torque here, because it is the kind of motion that is rotation. So, as force is needed for translation motion, torque is needed for rotational motion. So let us see what this term torque is. Now for defining torque, let us consider that O is the point about which this point P is rotating. So through O, the axis is passing, which is known as rotation axis. Now if we apply a force F here on P, so for rotation of P, if P has to rotate about O, it is not only the magnitude of force that is responsible. One more thing is important, that is its distance from the rotational axis or rotational point. And it has to be the perpendicular distance. So here the responsible factor is not only force to produce acceleration, it has to be force as well as its perpendicular distance from the axis of rotation, and this combined effect is known as torque. As it must be a vector, so torque is defined vectorially as R cross F. Now as you know that if we have to take moment of a vector, it is written as position vector cross that vector. So here you can see that torque also can be defined as moment of force. So this is how torque can be defined mathematically. Now if this kind of force is being applied on P, then we can consider a different kinds of cases which generally occur very frequently. The first case I can consider is when F is parallel to, let us consider the axis to be AB. So if F is parallel to AB, F is parallel to the rotation axis, that is AB. Now if F is parallel to AB, then R cross F has to be perpendicular to F. But since F is parallel to AB, so R cross F will be perpendicular to AB also. And then component of R cross F along AB will be 0. So it will not produce any kind of rotational effect. So to produce the rotational effect, there must be a component of R cross F effective along the axis, that is rotational axis. So this is our case 1. There will be no rotation here if AB is the rotational axis. Let us consider another case, case 2. Now here if you consider this is AB rotational axis, this is the point P, and now F is applied such that it can pass through the axis AB and let that intersection point be O. So what will happen then? There will be no perpendicular distance between the force and the axis AB, and in that case also torque will be equal to 0. So this also will produce the same effect, which is no rotation. Now let us consider case 3. Here we are considering that F is perpendicular to AB, but they are not intersecting. Now if I draw this situation, it can be drawn like, if it is the rigid body, let A be the axis here. It is the point P on which force is applied. They should be perpendicular to AB. So let us draw the force like this. Now here F is in the plane of this board and AB is perpendicular to this plane. So here if you write torque, then torque will be equal to, let this point be O, then it can be written as OP cross F. This time now you can see the torque is effective because it has a perpendicular distance from the rotation axis, and that can be written as this distance. Let that be OS. So OS is the perpendicular distance. So this result will come out to be, since we are writing vector product, so it has to be F multiplied with the perpendicular distance, that is equal to OS. So we will get an effective torque. This is the magnitude of torque. One more case we can consider. Let that be case 4. if F and OA are not perpendicular, so then we can take components of F parallel and perpendicular to the axis. Now torque of parallel part will be 0 and that of perpendicular part it will be effective. So you can see that this time again a torque will be effective. So here F and the axis are not perpendicular but they are making some angle inclined to each other. F and AB are inclined to each other and this inclination is not equal to 90 degree. This time also torque will not be 0. There will be effect of rotation seen here. So these are the basic concepts about torque. Today we learnt about rotational kinematics and then what is torque and then did some basic questions related to these concepts. In next session we will do some more elaborate questions. That kind of questions come in your competitive exams. By then, goodbye.